So let's talk about a situation where we know two sides and we want to use that to figure out an angle. So here we would be looking at sine theta equals 9/10. And from that, we could figure out a pretty good estimate of what theta is. By estimate, I mean an approximation, because we're going to have to round here. This is going to give us an infinite decimal. So there's an analogy that I want to kind of hark back to here, which is that when you have 2 to the x equals 3, the number that you raise 2 to in order to get 3, somewhere between 1 and 2, because 2 to the 1 is 2, and 2 squared is 4, so it must be between 1 and 2. It's not 1.5. We can kind of poke around and look at it, try to figure out what it is, but essentially and eventually we want to use inverse operations. Now for an exponent, that's rewriting this in a logarithmic form, which is that the log base 2 of 3 is equal to x. This has to be evaluated with a calculator, unless you're going back in time to the 1950s and using a slide rule. I would use the change of base here just to do log 3 divided by log 2. And that'll give me the number that gives me the exact thing that I want. So I take log 3 and divided by log 2. That's 1.584962.501. And there's more to that. Remember, every time you see something on your calculator, it's an approximation because there's more back there. Okay. Now, if I do 2 to the 1.58, it's not going to work out exactly right, but it's going to be pretty close. 2.989698. The more decimals I put on there, the more exact of an approximation, or approximation is a good word, that I'm going to get there. The point is that the inverse operation concept links this statement and this statement together. In the same way, we're going to link two statements together. This is the sine statement, and this is the inverse sine statement. Now, there is a name for the inverse sine called arc sine, but for most calculators, that's what you're going to see is just the sign with the little -1 symbol on it. So all I have to do is know how to use my calculator to do this. Now, my calculator, I type it in exactly the way I see it on paper there, which is I put in the inverse sine. I have to do second and then sine. Typically, the inverse sine of -1 is going to be a function button above, so little blue writing on my calculator. Then I put in 9/10, and it gives me this answer, 64.158. Now, I'm in degree mode, so I'll call this 64.2 degrees. If I was in radian mode, I would get a different answer because, of course, the radian and the degree number is not the same. So I'm going to switch my modes here. And I'm going to do this problem again. So now I get 1.119, so I'm going to call it 1.12 radians. So these are two different answers in two different units. You need to be clear which one is important for the context. We're still kind of focusing on triangles right now, so a lot of this is going to be in degrees, but eventually we should feel comfortable talking about radians as well. Okay, so let's take a look at a law of sines type of situation where that comes up, because that's where we encountered this. Was we looked at a triangle and I kind of backed up and walked away from it, but definitely possible that if we're given two sides and one angle, it could be that we're going to need that little trick to help us move forward. Okay, so let's say this is 18 degrees and this is 200 feet. So we know that we've got that angle pair. And then we've got this side, which is 400 feet. And we want to know what this is. So I'm going to call this alpha. And I'm going to say sine alpha over 400 has to be equal to sine of 18 over 200. So now I do my math, isolate sine alpha first. So this is going to be 400 times sine 18 divided by 200. I got to switch my mode back because I went into radian mode. I don't want to screw this up. Okay, so 400 times sine 18 divided by 200 is equal to 0.61. I'm going to keep a couple decimal here, so I'm going to go 618. And now I'm in a position where I can solve for alpha, because alpha is going to be the inverse sine of that. Now, I typically use the answer button if I can on my calculator because it really keeps me from having to round as I'm going here. But rounding or not, you're probably going to get something close to 38.2 degrees. So far, so good, because the size of this angle indicates that it's bigger side across from, which it is, this one. 18 degrees was 200 feet. So this side is bigger. Now we're at 400 feet. And really that means that the third side should be even bigger, because this third angle here would have to be 180 minus 38.2 minus 18. We're looking at 123.8 degrees. Now, the way I've drawn the triangle is really not to scale, because I've got this really big angle here. And this actually opens up an interesting ambiguity in the law of sines, which we'll get to in a second. So I'm just following through now. The missing angle would be 123.8. If I plug that in, redo the law of sines here. Question mark, or x equals sine of 18, 200. And so we're going to multiply, divide. So let's call this x. X equals sine, oops. $200 times sine 123.8 divided by sine 18. So that's equal to and that's 537.8, which is the longest side. Makes sense, because it would be across from the biggest angle. Okay, so there's the law of sines. Just going through the steps, you know, we found this missing angle. We used that to find this missing angle, and then we use that to find this missing side. So again, we can completely solve for the triangle given 3 pieces of information. I mentioned an ambiguity here, and this is something that comes up in the law of sines, because let's go back to this part where I had sine alpha equals 0.618, I think. Let me just double check. Yes, that's right. So sine alpha equals 0.618. Now, what we're going to discover later as we develop the unit circle concept is that this actually has an infinite number of solutions. Let me give you an example, and I'll just show you some possibilities. Let's say sine alpha equals 0.5. So when you use the inverse sign, what do you find out? Well, you should have found out that alpha equals 30 degrees. Okay, true. Alpha is 30 degrees, gives me a sine of alpha of 0.5. Now, just for fun, take alpha equals 150 degrees and plug it in and see what you get. Well, what'd you get? You find out that the sine of 150 degrees is also 0.5. And what happens if we put in the sine of, I don't know, how about the sine of 750 degrees? Turns out it's the same thing. So we've got this interesting thing, and this is one of the features of sine and cosine that make it so powerful, is that it's actually this repeating relationship where I can get more and more alpha values that give me the exact same output, 0.5. We're going to come back to that later. In this first part, I'm not going to give you any problems where you have ambiguity. You got to solve for multiple triangles. I'm going to leave that to the point where we've come and we've been able to develop our unit circle, so you'll know, given that we think alpha is 38.2 degrees, what is the other possible value for alpha inside of the range 0 to 180 degrees? Because that's, we can't have an angle in a triangle that's more than 180 degrees. So, but that's some interesting wiggle stuff coming up. Okay, talk about the law of cosines next.